Ladies and gentlemen, welcome to the second talk of mine this afternoon. While I talked about more military applications from military applications, I would now like to focus your attention to applications that have relevance in the civilian domain as well. I would like to speak about anomaly detection, and I would also like to create a bridge between the lower level fusion, which we have discussed so far, to higher level fusion elements. I would like to address the problem of tracking extended objects clusters, and finally I would like to give you an overview of emerging security and the civilian topics in which sensor data fusion is relevant. First of all, anomaly detection is an important part of situational awareness. We wish to focus the attention of users to situations which need this attention. And fusion-based anomaly detection is either unobtainable otherwise or exceeds what can be obtained by single sources in accuracy, reliability, or cost. Here I would like to give emphasis to simple examples and clear examples. I will not give a more general theory on anomalous behavior. So the key observation is that the methods of target tracking and data fusion actually have evolved into a fairly mature technology, but their full potential in situational awareness still needs to be realized. And this I would like to address under two aspects. I would like to draw your attention to classification-based anomaly detection and to violation of space-time regularity patterns. For this you will see. First of all, you have seen in the first lecture this morning these two figures. They show you that you can extract, even in a highly ambiguous environment, precision tracks, highly precise tracks, at the cost of some delay. And this gives you the possibility to draw in inferences based on retrodicted tracks. That means inferences on time invariant or slowly changing characteristics by exploiting scale and accuracy. An example would be retrodicted velocity histories. If you see a velocity vector 0 in your data, then you can be quite sure that you have a helicopter. And knowing that a helicopter is moving is relevant information, higher level information. If you look at the acceleration history, you can observe, for example, a normal acceleration of, say, 7g. This tells you that a fighter aircraft is moving, and it tells you also that this fighter aircraft can have no more underwing weapons. Yeah. So it's these inferences tell you something about the remaining threat level, actually, and belong to the higher levels of information fusion, and so on. Another class of inferences that can be drawn from multiple target tracks are related to mutual inter-object relations. For example, it's relevant at a higher level, at the threat evaluation level, to know if there's really an aircraft formation or convoy there. This has impact on threat evaluation. It's important to localize target sources and target sinks. Split-off events are important. For example, if a weapon is launched from an aircraft, you can use this information to classify this aircraft as an aircraft which is able to launch weapons, and you can even do a type of bookkeeping, giving you the possibility to estimate the residual combat strength, which has impact on action. That means has impact on higher level fusion. Stopping events we already addressed, and collective motion. The second aspect here in this context is the violation of space-time regularity patterns. What is a space-time regularity pattern? Well, a space-time regularity pattern could be, for example, a road map, a sea lane, an air lane. So if your targets are known to move on roads or lanes, this is a spatial regularity pattern which can be used. We have just seen how to bring in such information into the context of target tracking. Another type of such information is planning information. In a military operation, you often have fairly precise planning information. That means you have space-time information on how your objects should behave. If you use such space-time regularity pattern in the tracking, you can improve the track accuracy and the track continuity, and can improve the data association perhaps also. And moreover, you can test on pattern violation. If you know your targets are moving typically on roads, and if a road moving target is leaving a road, that's interesting. Or if you expect your planned operation is going on as planned, then a violation of this plan is interesting information and is an anomaly. Moreover, it's possible to extract space-time regularity pattern from the tracks. If you observe for a while a situation with ground-moving targets, and if you don't, with road-moving targets, and if you have no road map available, then you can actually use your the tracks of your road-moving targets to create fairly quickly a fairly precise road map of the underlying scenario. This shows the tracking techniques give you a possibility to extract context information from the tracking, and so on. I mentioned the term planning information. Sometimes, and fairly often, you have this planning information, especially if you are interested in blue force tracking. If you wish where your own forces are, your own military forces, or perhaps your rescue teams in a catastrophe environment, or the police teams in a police operation, where are your own forces? That's a typical question in the military domain, but also in the police and other domains. This planning information typically consists of space-time waypoints to be passed at given times via particular lanes. That is. And in addition to these waypoints, we have predefined tolerances. That means we have known covariance matrices for each individual waypoint and each individual object. We have these tolerances. If we have this, then the impact of the waypoints, if the plan is kept, is just given by this type of probability density function. In addition to the sensor data that you are processing, you have this planning information, waypoints, and corresponding covariances. This is equivalent, in a sense, to artificial data. So we can calculate these densities, and then it is easy to treat sensor data with timestamps before the waypoints are reached as out-of-sequence data. There are well-known algorithms to deal with out-of-sequence data, and this is an interesting application of out-of-sequence data processing within the context of exploitation of planning information. If the plan is kept, then this has impact on track accuracy, track continuity. We have seen how important track continuity is, and also on data association. If you have more information, you can exclude perhaps several hypotheses that had to be taken into account otherwise. Well, if the plan is kept, what can we do if the plan is not kept? If the plan is violated? Well, then the Bayesian formalism gives us the possibility to detect anomalies by pattern recognition, by pattern violation. The basis is a decision process. We assume two hypotheses and decide between these two hypotheses in a sequential manner. Hypothesis 1 means the observed objects obey an underlying pattern. Hypothesis 0 is this pattern is not obeyed. Off-lane motion, unplanned motion. As typical in statistical decision theory, we have two types of statistical errors. And then a good decision function is the ratio between the probabilities, the conditional probabilities of these hypotheses. Probability that H1 is true, given all the data, accumulated over time, divided by probability that H0 is true, given all the data up to the time k. If this probability is high and this probability is low, then the ratio is a very big number, and if the opposite is true, this ratio is a very small number. And if the ratio is something in between, we cannot decide. We wait for new data until we can decide. If we apply Bayes' rule to this ratio of probabilities, we immediately see that the key is this ratio of likelihood functions. This is a likelihood ratio of likelihood function, and this is the reason why this is called sequential likelihood ratio testing. If we calculate this likelihood ratio, we can do this with the techniques we have learned so far, then we have to calculate this ratio of two quantities. We have to combine the prediction with the likelihood under the assumption that the pattern is assumed, divided by the same type of information under the assumption the pattern is not assumed. that we have no planning information available, that there is no roadmap. Yeah? This can be calculated, and if we have the ratio, we compare it against the thresholds. If the ratio is large, we can be sure that their hypothesis 1 is true, no violation. If the ratio becomes very small, we know that there is a pattern violation. So anomaly detection can be formulated by a sequential likelihood ratio test using the methods that we have. So there are papers, if you wish, you can look up those papers. And we are speaking of higher level, of the link between higher level information and lower level information. We have addressed in the last lecture, before lunch, GMTI tracking. And sometimes it's not possible to create long continuous track. But in this situation, we often have human reports. Well, the human being is a sensor in a way. And what he reports, yes, is also a type of sensor report. And it is quite beneficial and quite necessary to combine GMTI data and human reports. Not so easy because, well, human beings are no technical sensors. This leads me to give you information on a NATO task group. This is a NATO event. Therefore, I would like to show this. It's a task group that has exactly this gap between higher level and lower level fusion as its objective. This existing bottleneck between real-time device-based information that we obtain by sensor data fusion and higher level information, which is mainly based on textual information, human reports or something like that. Bridging this gap has enormous benefits, and the novel approach we plan to achieve with this task group is to explore the potential of battle management language as a unifying framework to represent all the different levels of information. Battle management language is a language which is used in the military domain. It is a language which has much smaller scope than natural language, and it's a language which can be understood by both, by human beings and by computers, and that's the trick. If it's possible to represent by a battle management language all the contact information available, if it's possible to represent the sensor data fusion results in this way, in battle management language, and if we formulate human intelligence, open source intelligence, and soft data sources in such a way, then we have a possibility to make a combination of higher level and lower level fusion by computers. So that's just to give you an insight in ongoing work. We will base this work this is the context of magic, and I'm very glad that we also have a Turkish representative in this task group. So that's ongoing work. So you see that's really ongoing work. It starts next week in Paris. So it's really topic and up to date what you are seeing here. So the next step I would like to address is expanded objects. So far, and for the rest of the meeting actually, we will treat with objects that can be modeled as point source objects. Often, however, we have no point source objects, but we have extended objects. An extended object is, for example, something like this, or a group of objects which is partly resolved. Resolution, important topic. We have discussions during lunch about the resolution. Extended objects typically produce more measurements than only one. There are many scattering centers, and a single object produces more measurements than only one. The same is true with a group of targets. They sometimes, when the resolution conditions are good, they produce as much as measurements as the objects are there, but often much less measurements are produced. And in extended object tracking, we wish to we wish to learn more than just the kinematic properties. We wish to estimate the shape of the object. And one first and useful step towards this direction is to approximate the shape of extended objects by ellipses, or ellipsoids in higher dimensions. So we are interested in estimating the position and the kinematic properties, and we wish to estimate an ellipse, yeah, an object shape. That's the idea. How to do this? Well, before we do this, I would like to give you an example from the ground surveillance world. Convoys are important objects of interest in ground surveillance. And under variable resolution conditions, well, it's not easy to do that. The users are interested in three quantities, actually. They want to have the kinematics of the centroid, a vector which describes the kinematics. They want to have an estimate of the extension, and they want to have an estimate of the number of vehicles involved. Since there are resolution phenomena, estimation of the number of vehicles is by no means easy. In the talks of Peter Willett and Roy Strike, you will learn techniques that help you to estimate numbers of targets involved. We here use cardinalized PhD techniques. You will learn what a cardinalized PhD technique is from Peter Willett and Roy Strike. And here, just as an example, illustration, a convoy is moving here on this road. We have good resolution conditions. It's easy to estimate the number of targets involved, 7 in this case. Here we have an intermediate resolution with only a few measurements. So we have here easy, not so easy, but .69. But even in this case here, then the target has a very bad sensitive target geometry when the resolution is dominated by the cross-range resolution, which is poor in a GMGI context. We only have one irresolved plot, and it's possible to estimate even here, or to keep the number of the estimate somehow alive. So let's go back to mathematics. What do we have to do? We have said that the state of a quantity collects all that is interesting for us at present. Well, if we are interested in the object extension, we must extend this state, well, by what can describe an ellipse. Well, an ellipse is mathematically described by a matrix, by a covariance type matrix. Yeah, this is an ellipse is defined by a symmetrically, positively defined matrix and a center. And so this is the idea: extend the object by considering random matrices. So we have a random vector for the kinematics and a random matrix for the extension. And we wish to integrate context information, Doppler blindness, roadmap information in this context as well. Well, let's look perhaps at this notion of state, perhaps. Well, which object properties are of interest? We collect them all in the state. So x, k at time k. And these are some examples. We have seen already the example of a road moving target. So here the state is very simple. We have a real number, the odometer count, and the temporal derivation of it. Yeah, it's very simple. In a three-dimensional space, we have a 9-dimensional state vector. 3 dimensions for the position, 3 dimensions for the velocity, 3 dimensions for the acceleration. We have joint states of several objects if you wish to track formation. We have seen formations that are to be tracked. Sometimes we are interested in attributes. That means we wish to have the kinematic properties, and we wish to have an estimate of the radar cross-section. This belongs to the state. Yeah? Positive real number and a vector. We have also seen this, maneuvering phase. So we have the kinematic state and the maneuvering phase, yeah, in this IMM context. And here, what is new here is, in the same philosophy, we do extended object tracking by looking at a vector for the kinematics and a random matrix for the object extension. And with this, we go into this Bayesian estimation scheme. We wish to calculate these conditional probability density functions of the full state, which is a joint state now, kinematics plus extension, and this conditional PDF describes what is known about the extended object based on all the sensor data up to and including time decay. And what is extended object tracking? Extended object tracking is calculate iteratively this PDF. That's extended object tracking. Quite clear, and this is sort of a repetition of what we have learned this morning. So we apply Bayes' rules and look carefully at the densities we have. So I said we have densities here. We have joint densities, and according to the little rules we have discussed before noon, we can rewrite this joint density as a product of a vector variance density and a matrix variance density. Yeah, this is possible. There is literature on random variables that are represented by matrices. The likelihood function contains all the relevant information for estimating this joint state. For getting useful algorithms, it makes sense to restrict the class of probability density functions to which these individual factors belong to. We assume, in the same sense as we do this in Kalman filtering, we assume that the vector variate part has a Gaussian character, is a Gaussian, and let us assume that the matrix variate part is also from a special class of matrix variate probability density from inverse Wishart densities. These inverse Wishart densities are well known to the statisticians, and we can use them as trackers in data fusion people. Now, let us look at the likelihood function. Well, I said for a standard object, the likelihood function actually consists of is created from many measurements. We have not only one measurement or no measurement, we have several ones. Let's assume we have n measurements, and that means the likelihood function is a product of n measurements, assuming independent data in this case. If you look at this product, you can do by calculating by some algebra, you can rewrite this product in the following form. This product can be written in the following form as a Gaussian multiplied with the matrix variate density, which has the form of a Wishart density. It's a known class of matrix variate densities. And the Gaussian part has this as a measurement. It has a centroid measurement, the arithmetic mean of all the individual measurements, and the Wishart part has the scattering matrix as a measurement. So we interpret this likelihood function as two effective measurements, one centroid measurement and a scattering matrix, in this form. And with this representation, we go into the Bayesian rule. The Bayesian rule tells us that the density after filtering can be written as likelihood function multiplied with the prior, the prediction. And with this structure we have just seen, a special form of the likelihood function, a special form of the prior, we see that the update here consists of four factors. We have one factor which is a Gaussian, and which is essentially what we obtain by Kalman filtering. So it's a Kalman update essentially. Then we obtain a factor in which the innovation matrix appears. Innovation matrix, so we call it, has this structure, and it is very similar to the innovation vector in Kalman filtering. In Kalman filtering, it's a vector which consists of the measurement and the prediction, and here we have a similar structure, but we have a matrix. Here we have the transpose here, this is a matrix, the innovation matrix, and we have here the factor which comes from the likelihood function. This is the inverse Wishart density that we have assumed from the beginning. If we rewrite this product of three factors, we end up with the following representation. We end up with the filtering update, which gives us the extended objects track as a Gaussian multiplied with an inverse Wishart. The Gaussian is characterized by parameters, which are obtained by the Kalman update formula, and we have here the inverse Wishart with parameters. And for these parameters, we have also simple update equations. So that means we can extend the notion of Kalman filtering to extended objects by adding random matrices for describing the object shape. And this is the thing we have to do in addition. We have in addition to do update equations for the object shape. In practical applications, we are often interested in estimates of the kinematic state of the object only. So that means we have to calculate the marginal of this joint density. We have to integrate over all random matrices to get a probability density function of the kinematic properties only. This is often kinematic properties are relevant. So we have to write here this extended object track into this thing. And the nice thing is that we can integrate over all random matrices in a very easy manner actually. By standard algebra, we can transform this product of two densities, a vector variate density multiplied with a matrix variate density, into another product of a vector variate density multiplied with a matrix variate density, in such a way that the random matrices here do not appear anymore in the vector variate part. And we can draw the vector variate part before the integral, and remaining is an integral over a matrix variate density. Since matrix variant densities are normalized, this integral is 1. Yeah? So just by algebraic calculations, we can evaluate this integral. And it's interesting what comes out of it. Well, the marginal is a well-known density in statistics. It's a multivariate student T density with new degrees of freedom. And this is the basis for kinematic target state estimates with related error covariances. It's a basis for calculating expectation gates for extended objects. It's a basis for extended object track-to-track correlation for fusion, and so on. So all the machinery that we have developed for point source targets can be extended to extended. Before I end, I would like to give you an example, a simulated example here as well. We have here a formation. A formation is an example for extended targets. We simulated the partly resolved measurements obtained by a radar sensor, for example, here. And what we are doing now is we track this formation over time and calculate estimates of the kinematic and estimates of the object shape, the object extension. So we obtain a vector and a matrix, and between these two ellipses we have here in the middle the matrix, and the lower and the higher is, so to say, a generalization of the covariance of an ellipsoid estimate, the covariance of a covariance situation. After a while, the formation splits off again. The ellipse begins to become eccentric, and this is the time to split the extended object track into single source tracks again. This is what I wanted to say. Here there's some work done here. Also, it's possible to embed all this into a multiple object tracking framework, exploiting expectation maximization, and a method that was proposed by and is developed by Roy Stride for ballistic process tracking. Now I would like to look at some civil applications. For this reason, I have to switch from LaTeX to PowerPoint, which is perhaps a bit systematic. And let us see how we can apply all this in a civil application. Actually, the London terrorist attacks have inspired us to do so. Well, is it possible to apply the military techniques we have developed over years to help those people? Those people have a complex situation, a complex surveillance task. They have to deal with rare events. A terrorist attack is a rare event, but if it happens, it's really dangerous. And it's really a difficult job, and we have to focus the attention of these people to anomalies. We spoke about anomalies already. So we need what we call an assistance system, yeah, to focus the attention of the security personnel to dangerous persons. For example, this guy. This is a photo taken from the London Tube underground, and this is one of the terrorists, and before he made the attack. And actually, he's carrying here a bag, and in this bag he has explosives. If it were possible to tag them, like here, it might be possible to prevent this attack. In a couple of minutes, he will cause the death of many people, and his own. Yeah? What can be done? Well, what makes this man look anomalous is not that he looks down, but the anomaly with him is he's carrying explosives, and a fairly large amount of explosives. Explosives can be detected by chemical sensors, technical equivalent of our noses. The problem with chemical sensors, however, is that they have a very poor resolution. We mentioned the notion of resolution already. It's a very important notion. So resolution, well, it's the same with chemical sensors, the same as our nose. If we smell a perfume, for example, then it takes a while until we realize this is the person is gone. We are not able to associate this chemical signature to an individual. We are not able to localize it. We are not able to track it. What can be done? Yeah. So that's the problem. Well, the solution to the problem might be the following. Well, if you go to these public areas, you always have access regions which have a reduced complexity. But in this situation here, let's go back. Here, it is too complex. But to get there, you need to pass escalators. You need to pass hallways. You need to pass tunnels or something like that. And these tunnels give you the chance to gain time and space. You gain time if you are able to track all the individuals that enter into such a tunnel, walk around and leave it. It gives you time. And you know in the tunnel where are my people. And space is that you add more than one sensor. Chemical sensors have the potential of being cheap. You can equip the wall with several sensors. And then data fusion means combine the sensor, the output of all the chemical sensors with all the tracks of all persons at each instant of time. Yeah? This is data fusion. And data fusion, therefore, is a means to compensate poor resolution by adding time and space, by adding data, actually. We have proposed this to the European Union and won the project. The project has the name HAMLET, Hazardous Material, Localization and Person Tracking. And this is the more general idea of a security application. Well, the idea is use all the military techniques to help the security personnel here. So we have here the tunnel. The tunnel is equipped with sensors that allow you to track the persons. And you have attribute sensors, chemical sensors, biological sensors, radio, active sensors, for example. All these sensors have the same problem with resolution. Now let us look into the mathematics a bit deeper. So we have here a process in which we have a tracking task and a classification task. We wish to classify the people that we are tracking. And we wish to classify while we are tracking them. Therefore we have a combined tracking and classification task. Yeah, that's the trick here. So we have to get the kinematic state of the observed persons, and we discretize the output of the chemical sensors in such a way. We created 5 levels, and the task of classification means calculate a classification matrix. The classification matrix has here the alert levels and here the persons, and each entry, this one for example, tells you the probability that person number 3 has the attribute orange. And those persons who have the attribute dark, red, are terrorists. How to get this? Well, due to the low space-time resolution of these sensors, we have a non-trivial association task. Yeah? We need algorithms that do the association. So we have fusion, we have tracking, we have fusion, we have classification, we have association. So all the key ingredients of our science are in this problem. And the task is, well, who is carrying the bomb? This is a simulated example. Let us discuss this a bit clearly. We use to solve the association problem a technique which has been proposed by Roy Stride. Peter Willett will address this in his talk today and several times. It is called probabilistic multiple hypothesis tracking, PMHT. The trick here is that we replace the data association problem of standard MHT with an iterative procedure working on a sliding data window. And the key of it is expectation maximization, a statistical technique which is actually a clustering algorithm. And the application of this clustering algorithm to tracking means is that we wish to cluster over time. Yes? And the data association hypotheses become random variables which are estimated by this expectation maximization. So this method is well understood. Let us apply this to this chemical sensor. The key ingredient of applying PMHT to classification is to calculate a quantity that we call the relevancy. The relevancy of the output of chemical sensor 2 at time 4, here for example. And we have to calculate it for each instant of time. We have to calculate the relevance not only for sensor 2, we have to calculate it also for chemical sensor 1, for chemical sensor 3, and for chemical sensor 4, and for chemical sensor 5. We have to take the relevancies of all sensors for all persons over all time. Not only for person 3, also for person 3, also for person 2. And that's the key. Take everything into account. And then apply this data, this expectation maximization technique. This technique allows you to calculate an estimate of the classification matrix here. You have it is necessary to go into the papers to understand it more clearly. But expectation maximization is the key to do it. So we did this, and well, theoretical approach. This gives you an idea of how to work. Theoretical idea, realize it in a simulation, but then the practical people come and say, no, that's not possible in practice because you have velocity and the turbulence and the temperature and the delay is also so complicated. So the next step in such a project must be to create a demonstrator, to go from the simulation to the lab and to build it in a simplified way. And this is what we did. We created such a tunnel, from wood. It's easy to drill holes to make something in it. We equipped it with 4 chemical sensors. We equipped it also with radioactive sensors actually, and we had laser scanners. We had 3 laser scanners to track the people. We had here a laser scanner, here a laser scanner, here a laser scanner. We used the laser scanner because it's so easy to deal with them. The robotic people are using laser scanners always. It's much easier than to do video tracking. It's possible to do video tracking also. You need the tracks. What type of sensor or ever. Laser scanners are simple and good actually. And now I would like to show you what happens. Mouse. This is a movie from a lab. But these are just cameras which just gives you an impression. These videos are not exploited. Exploited are the laser scanners here and the chemical sensors here. And here you see the output of the chemical sensor. Well, now people are entering, sorting around, they are tracked, and the output of the chemical sensor is processed. This is the situation. So we have a tracking process, and as soon as nobody is carrying a bomb, well, nobody carries a bomb in our lab, but carrying an explosive, which is substituting bomb, nothing happens. But at a certain instant of time, we do not know when, or well, I know when, but you do not know when, the person is entering and look at this one. He was the dangerous man. In the beginning, it was not clear who was dangerous. But he is carrying the bomb, and over time, it's quite clear. So let's pick out him and look what he's carrying. The nice thing. Another example. We made several examples. Here we had a similar situation, a little bit different. We put emphasis on something different. Also, persons are strolling around, and somebody is carrying a bomb. And the nice thing of this type of solution is that it has an inbuilt law compliance, because all those people who are not carrying a bomb are not seen at all. Who is not carrying it? The system is blind to those who are not carrying hazardous materials. And only those who are suspicious, they are tagged with a red circle and have to be processed at a greater detail. Well, this one is the guy. It takes a while until it's clear that it was he. It's possible to get him. The last example. Always quite different situations.
Sorry, what happens if they switch the bombs on the way?
If they switch the bombs, then you need another guy who is your companion. Yes, next research topic. If you have a cup, if they switch the bombs, then it's of course, that would be a strategy. But typically they do not know when they are observed. These chemical sensors can be hidden in the wall, and nobody knows that he's looked after. you're right. It's a long way to come from this to... Well, this is like electronic countermeasures and electronic countermeasures and electronic countermeasures. It's good for us researchers because we always have something to do. But this is an idea. It shows you many aspects. It shows you heterogeneous sensors. Nothing can be more heterogeneous than a chemical sensor and a laser scanner. Yeah? It's a fusion of two questions, actually. We have the tracking question and the classification question. Here, both have to be solved simultaneously. Yeah? And we have, yes, so it's an example. Well, there is something like dual use. Typically, dual use is from the military world to the civilian world. Here we have the opposite. A civilian-funded project had interest for the military people as well. We used it in a NATO exercise. We are here in the NATO event, Common Shields, to do it for camp protection, harbor protection. So there's something actually to be done. The lesson that we learn is the full potential of CBRNE sensors, chemical, biological, radioactive, nuclear, explosive sensors, can only be exploited in a sensor fusion approach. It's a wonderful thing for us. And this shows you that sensor data fusion, the topic of this lecture series, is highly a hot topic, and it's quite correct that there are so many people here. This gives you an insight of what we are doing in our thing. We are actually much interested at present in radioactive sensors, quite an interesting class. And we are currently redesigning it and making it bigger. And it is meant to be used for camp protection. So another thing which is in between the military applications and the police applications, the civil applications, is emitter localization. Emitter localization for an unknown number of objects, localize and track an unknown number of three-dimensional objects, radio emitters from two-dimensional data, from bearings, for example. Yeah, that's an important task for military users, important task for police, important task perhaps also for first responders in a catastrophe scenario. So that's really relevant. Let us look here first to the platforms we are considering. We are consulting agency to the German MOD. This means we are providing work also for big UAS, for this Eurohawk, which is for signal intelligence, and Barracuda, which is a combat exercise. Here in our lab, we have exercise to these systems. We have a helicopter with a payload of 25 kilograms. This gives us a possibility to do experiments without thinking too much on miniaturization. And we have smaller ones, which gives us a possibility to consider combined operations. This is an important German military tactical UAV, the Luna system, and we rarely do experiments with operations, with fielded military systems. But here we created a pod, and with this pod, which was under the wings of an ultralight airplane, we do experiments. Emitter localization, this slide shows you the radio frequency sensors we are taking into account. For the Luna, we actually built a direction finding sensor ourselves. Here the problem was that it had to have a very small aperture. That means all the intelligence must lie in the subsequent signal processing and using higher order statistics, for example, to increase virtually the number of elements involved. Very important also was the correct calibration. You see here the Luna is our calibration camera, the interaction of the sensor and the platform. You see here the same idea, the spiral antennas, which have a much higher bandwidth. You see here antennas which enable us also to measure polarization. You see here an array antenna with several arrays, Vivaldi arrays. So such antennas typically are heavy, too heavy for, say, 5 kilograms or so, or heavier, too heavy for small tactical UAVs. Better suited are the sensors like this. This is a TDOA sensor with a blade antenna here, time difference of arrival sensors. Time difference of arrival is in greater detail. Here you see experiments we have done last year in Spatzenhausen. That's a proving ground in Germany. The military people have hidden here 3 emitters in the ground, and the Luna had to fly and had to localize them. during flight. I would like to show you this movie. So that means here fusion means to collect bearings. That's not work. Sorry. Well, the Luna flew around, collected measurements, and theta fusion means to fuse all these bearings to find here these localizations. With radio frequency sensors, you are limited in your resolution, typically and fundamentally. If you wish to increase your accuracy, position accuracy, you need other sensors. For example, sensors who are known to have a good resolution. Here, for example, the cameras. Cameras have a high resolution sensors. And the good idea is to combine these two types of heterogeneous sensors. Radio frequency here and cameras here. Cameras cannot measure audio signals. They are ambiguous but accurate. They can measure radio signals. They are unique but are not accurate. Good example. And these slides show you the principle. Well, fusion of signal intelligence with image intelligence, you can extend it also to SAR, mini-SAR, for example. So let us assume we have here a lunar UAV flying, and after a while it is producing from collecting all the bearing measurements a first localization characterized by this ellipse or by such a probability density function, a first coarse information on the position. Then you use this first coarse position information to direct an image sensor. This is the footprint of an image sensor. And then by segmentation techniques you find in the image all those groups of pixels which have a chance to be man-made, to have a chance to be an emitter. And then you combine these results with the finding of the direction finder, and then gain in accuracy and lose in ambiguity. You get probability density functions which are spiky but ambiguous. But you have won something. And over time, there's also an aspect of fusion. Fusion over time is also an aspect of fusion. Over time, if you fuse all these things, you end up with more and more accurate data. And with such much more precise localization, you can do something. You can distinguish in which story of a house the radiation comes from, or in a car convoy, the second car, not the first, not the third. There's also a high enhancement potential for already deployed systems. We did, just to show you ongoing work we have, we will present this work at Fusion 2011 in Chicago in the week after the next week. To find cars in the image. This addresses a filter which will be introduced by Roy Streit in his presentation, the so-called intensity filter, which is based on Poisson point processes. In the regular order I would have given this presentation after Roy's paper. So this is an example already, and we already see an example of the method we will just learn. This intensity filter. It is the big advantage of this filter is that it allows also to estimate the birth rate in arbitrary scenarios, and the clutter models in both methods. It is based on a paper Roy gave in Fusion 2008 in Cologne, and I think it's the first practical implementation of the intensity filter that is already will be published at Fusion 2011. And if you have the chance to go to Chicago, please see this visit, or if you are just in the paper right now. And we have also made field trials. I think the first field trials that exploited Roy Streit's Poisson point process filter last summer. We used an ultralight aircraft with these pods. These pods model an unmanned aircraft. So this is, so to say, a unmanned aircraft. We used this emitter sensor and a standard camera, and you see here a particle filter representation of the intensity function. I told you this morning that it's important to look at functions of state variables. The intensity is another function We have seen probability density functions. Intensity is related to this, but quite a little bit different, and you will learn from Roy's tribe what it is. But this is the image of such a density, and here where the particle filter clouds are dense, we expect the emitters. What is interesting to know is that we could experimentally verify a fusion gain and position more than a factor of 6, so it's really relevant to do the fusion of radio frequency and cameras. And if you put more emphasis in the calibration and all this dirt, blood, and sweat work, then you can increase it even more. I would like to discuss this aspect of multiple aerial systems a bit more. If you have more than one platform, you can look also at time difference of arrival measurements. If you have two platforms, you can measure time differences, and from time differences, estimate locations. You can combine it also with direction of arrival measurements, and this is a large potential for fusion. It's also possible to consider the cooperation of platforms with heterogeneous payloads. You have seen this with image sensors and so on. It's an interesting fusion task also to look at the combination of fixed-wing aircraft, lunars, for example, or copters. Copters can hover, have very different properties, and it's a nice application to design mission rules to reach your surveillance goal optimally by using these two types of platforms and making use of their individual capabilities. It's also an aspect of sensor data fusion. Yeah, it's very, very necessary. Let us look at time difference of arrival. You see here this example with the direction of arrival measurements. You can, if you collect them over time, you can provide an estimate of the position. If we have here an airborne UAS, and here a stationary sensor, which is on the ground, which can be very small, which can be very cheap. These sensors are much smaller than direction finding sensors. You can compare time differences between this stationary platform and the moving platform, and this creates a hyperbola. Each time difference of arrival measurement is equivalent to a hyperbola, and the localization means bring all these hyperbola over time into intersection. That's fusion in this case. Interesting is it perhaps also to combine two different platforms. A high-value platform, here for example, a high-value platform which is carrying a direction finder and a TDOA sensor, which is small, and combine this with a small platform, a cheap platform, which has only a direction, TDOA sensor. Then you can combine a bearing with a hyperbola and instantaneously localize the target. This is relevant in situations where the message is small, is short. If it's only a short message that is sent, then you can localize it with two platforms, or with 1.5 platform, one moving platform and one stationary platform. This is an example here from a military project we have in cooperation with industry. Eurohawk is a big signal intelligence sensor. If with this sensor the tracks of maneuvering targets are to be estimated from directions of arrival only, the tracks are very poor. Sometimes they are quite good. This one is good. This might be maybe acceptable, but the other estimates are wrong, really wrong. Yes, that's wrong. And you can help also with TDOA. I go to my last slide now. It is this one. This one. It is GSM. GSM base stations are interesting things. GSM base stations are mobile phone base stations. They're everywhere. It's a globally available infrastructure. And they can be used as illuminators for passive radar. As illuminators available even in out-of-area regions, in littoral regions. This is the coast of Norway, for example. And why not doing passive radar with GSM base stations as illuminators? They are everywhere, even along the coast of Somalia. That's our experimental system, our Gamma-1 system, the stationary Gamma-1 system. We can look with the system in the region, and we have observed in our first experiment a road which is here. And here is the range Doppler plot for a bus target, our bus in the range Doppler cell, right cell. Here we have vehicles of opportunity, car convoy, and here a car passing by. So with GSM passive radar, it's possible not only to look into the air, but to use it also for perimeter surveillance, border surveillance, something like that. If you wish to observe something, and if you don't wish to build up a radar. Yeah. This is an experiment we have done with the TRANSALL Aircraft. So this was the two base stations as illuminators. Fusion in this case means bring ellipses into intersection. Yeah? So we cut hyperbola, a few slides before. Passive radar means intersect ellipses. That's fusion. Passive radar systems will be hybrid systems that use different and complementary illuminators that use electrosmog of all forms, so to say. And due to the omnipresence of GSM illuminators, there are many applications beyond what we already think of. This is our mobile experimental system we built up. With this experimental system, we go to the German coast of the North Sea. These are experiments that will start in July. With the infrastructure along the North Sea, we wish to observe this area in the German North Sea. We wish to observe ships there. And I hope in fall I will be able to report about interesting results. This offers the opportunity of blue border control, for example, without creating much infrastructure. Yeah. The infrastructure is there, GSM base station. You only need a passive sensor. Thank you very much. Any questions? Yes.
Very early, very interesting transfers. We are talking about the trackers and to calculate the likelihood value in the sensor.
Yeah.
Which one is the useful method to calculate this value in the sensor or in the tracking software?
You mean the architecture?
Yes.
Yeah. This depends on quite on the applications. The concrete fusion architecture is very much project and application driven. There's not a general solution. Much depends on communication, for example. If your communication is a scarce resource, then you have to do as much as possible on board and to send only pre-evaluated results. The problem is if you are doing too much onboard processing, you do not develop the full potential of fusion as if you could send the data in a more raw form to the station. So, for example, in the ship example, we have an activity called multi-platform engagement capability. Sensor data fusion crosses platform. Two ships. One ship is attacked by a sea skimmer, and if you do individual sensor data fusion, then each sensor tries to extract the sea skimmer, and it's hard to see the skimmer early. If you do the track extraction on the data set provided by both sensors on the raw data, you can extract the small target much earlier. The price is higher bandwidth for communication. So it's always a trade-off. In a given military application, you must analyze what are your constraints, and depending on your constraints, you have to design a fusion architecture. And this is typically a hybrid solution. Some things are done on board, some aspects are done in the fusion center. This is we should talk about concrete problems. So that in reality we must be very careful. There does not exist a generic fusion system which can be used for all applications.
The other one is today is nowadays sensors is not a qualified output. I mean that we have a plot, but this plot has not a qualified value, and the fusion sensor, while this fusing this plots or data, it's not used any value about the sensor characteristics. So if we build a new sensor, is it suitable to request from our scientific person to give a qualified plot or likelihood values to the fusion center.
If I understood correctly, it's often actually made the same experience. If you are working with real data, then the manufacturers of sensors does not tell so much. You need parameters. If you wish to process sensor data, you need information about the quality, the measurement accuracy, the resolution, detection probability, other things. Yes, and typically they do not give. They are often refusing to give out even the measurement. They have some internal track processing and give out pre-processed tracks. This is a bad thing. And if you are designing a new system, you must force your manufacturer to give you the measurements and to give you the parameters that describe the quality of the measurement. It's very necessary. Data fusion without a context information, without having an idea of what the measurement accuracy is impossible. Yeah, so but I know it from its own experiments. I saw data which were just data, no information on the quality, and it's very hard to do something. Well, it's possible then if there are some things can be estimated actually over time, and it's possible to do something. But the best thing would be to make sure that the quantities that are relevant for likelihood functions are somehow known. And I know in practice it's often a problem. Because manufacturers do not wish that other people know how good or how bad the sensors are.
The last one is
perhaps you could discuss outside because we are running late. Sorry.
That's good.
Thank you.
No break now, right?
No break.
Everybody's still awake? Still awake?
We'll have a break after you.
Okay. Not to last for an hour, and then we'll have coffee. So, 2 times. Okay, well, there's no feedback here, right? You can stand here. So, I hope you're enjoying the lecture series so far, and it's not too tiring. What I'd like to do is, let's see. Well, the motivation for data fusion, I think you've heard a lot of great examples from Wolfgang so far today. So the only thing I would add is to say that the basic task, regardless of whether you, no, I do hear feedback now. You can stand over here. Regardless of whether you have a military threat or a civilian threat or any other of a number of tasks, it could be a medical application. The general trend is that we have increasing numbers of ever cheaper sensors. We're swamped with data. We all know this from our own personal lives also, right? A lot of data coming at us. And what are we interested in doing? We're interested in collapsing all of this data across sensors. That's sort of what you might think of as the traditional data fusion, but also over time. So target tracking is really just data fusion over time. So as to do what? Well, so as to take voluminous data and collapse it to a small number of objects that hopefully contain a good mapping to the objects of interest. So you want to extract a small number of objects, but you'd like to do so in such a way that these objects persist over time and that they contain the objects that you're interested in extracting. So here's just an example. This is multi-static active sonar data. It doesn't really matter what, this is simulated data. But the point is that you're taking a large quantity of dots on a screen, and it turns out that you can work on the signal processing problem. You can try to improve the processing that you have in any given scan of data to get slightly better SNR returns. But it turns out that if you start reasoning over time, that's what target tracking is all about, then even with a fairly simple tracker, this example actually, this is a global nearest neighbor tracker. You'll hear more about this language later. But it's a simple track management and filtering scheme, and it can perform remarkably well because we're reasoning over time, and we're removing many spurious false returns and attempting to associate the good ones into tracks. Now, if you associate the good ones into tracks, several good things happen. First of all, you obtain objects that persist over time. The localization also generally will be better since you're associating and filtering objects over time. Although there's no guarantee that you'll do so. It's possible that I associate good contacts, but that I also include some false contacts. So in principle, there's no guarantee that a tracking solution is better localized than the detections that go into the tracker. But generally speaking, that's what you'll find. Here's just another example. This is actually, this is from an old active sonar sea trial with a submarine target. But again, the same message, that if you like the complexity associated with tracking, you can have a lot of fun with it. You'll hear many things later today and tomorrow. It can get very complicated, but the good news is that oftentimes even a fairly simple tracking solution can give you remarkably good results. Okay, so this is an outline of what I'd like to try to touch on very briefly today and tomorrow. And I'd like to start by sort of going back to basics. Okay, and so let's start talking first of all about target modeling. So how should we model and I'll talk in the context of kinematics, just to keep it simple. Let's talk about the motion of objects. How should we model the motion of an object? Well, what you heard from Wolfgang and most of what you'll be hearing in the rest of the lecture series involves stochastic motion models. Why stochastic motion models? After all, the object that we're interested in tracking may have a deterministic trajectory. There's somebody driving a tank or a plane or a submarine and is following a prescribed plan possibly, and so there's a deterministic behavior. The reason why we use a stochastic motion model is that generally speaking it's the easiest way to model uncertainty. Much like if I flip a coin, you could study with a very complex deterministic model and try to estimate the probability of heads and the probability of tails, and you might come up with a slightly improved estimate than the one that I would give you, which is 50-50. It's much more complicated. So that's sort of the underlying motivation for looking at stochastic motion models. And so let me just very quickly, and don't worry about the details of the equations. It's difficult to absorb this in real time. But let's just talk about this at a high level. So the simplest model you could imagine using is a nearly constant position model. This is everything I'll be saying in this first set of slides is in one dimension. Okay, so we have an object, and that object is moving in one dimension. And as I said, the simplest model that you could adopt is one that says, well, the position of that object is perturbed by a white noise process. Okay, so that means that I'm standing here, and over time, I sort of drift left or drift right, and my state is position only. There's no velocity in my state. So that means that where I am, there's actually no velocity defined for the process, even though I'm writing the kinematic motion model with an x dot with a derivative. In fact, the state of the process is only position. Well, so this is written in continuous time. So this is maybe another important point to emphasize, which is that oftentimes if you look up papers on target tracking, you'll see discrete time motion models. And that's fine, but generally speaking, if we're talking about objects moving in physical space, you really should be starting in continuous time. And it's okay to discretize, because then, in fact, we're going to take discrete steps in time, and we do so, but it's important, at least once, to go through the process of going from continuous time to discrete time. Why? So that when you write down a discrete time model, you have the right dependence as a function of time. And in particular, with this nearly constant position model, if we discretize, so we integrate both sides, what do we get? Well, we get that the position of the object at time k plus 1 is what? It's the position at time k plus perturbation. How much perturbation? Well, it's a zero mean perturbation, and it has a variance that grows linearly in time. So is this a good motion model? Well, it's a pretty simple model. That's good. It doesn't have velocity defined, so if you had an application where you're measuring Doppler, for example, you wouldn't be happy using this sort of motion model. And the other thing is that position grows unbounded over time, which, depending on the application, may or may not be problematic. Okay, so you could say, well, let's make things a little bit more complicated. And actually, by making things just a little bit more complicated, you get to the motion model that is the most commonly used in the target tracking and data fusion community. That's the nearly constant velocity motion model. So here it is, written again, starting from continuous time. And the state is now the position and the velocity of the object. And so the change in position and velocity is, well, we've got a matrix telling us that essentially, so the derivative of the position is velocity, and the velocity is just the velocity plus, well, no perturbation when written in continuous time. And the acceleration is the white noise process. So essentially what we've done is we've taken the previous model, and we, rather than thinking of that as a positional state, it's a velocity state, which then gets integrated once to result in position. Okay, so again, what do we want to do? We want to discretize that model. So we start from continuous time, and I'll skip the details, but they're here, so anybody that offline wants to look at it can see the details. And well, it involves the matrix exponential, which there are various ways to compute. But the bottom line is that once you discretize, what do we get? Well, we get that, again, x is now position and velocity. It's the position and velocity, well, it's linearly dependent on the position and velocity of the previous step. So the A matrix is this. Okay, the discretized transition matrix is this. What does this tell us? It says, well, the position at time k plus 1, it's the position at time k plus the time step times the velocity times k. And the velocity at time k plus 1 is the velocity times k at time k. So that's without any additive noise. This would be a noise-free model. But in fact, we have an accumulation of noise that amounts to zero mean noise and a covariance where the velocity uncertainty grows linearly in time, just like the position in the simpler model. But it turns out that the positional uncertainty grows as time cubed. So again, it's useful, I think, to see this so that people will generally start here, and it's good to know where this comes from. Okay, again, we'll skip the details of the discretization. And okay, so do you like this model? Well, it's still a pretty simple model, and we now have a well-defined velocity, which is good. Again, if we have, say, Doppler measurements. But position and velocity grow unbounded over time. So if you were to simulate the motion of objects, you want to test your algorithm, and you're going to generate many target trajectories, and you have these targets obeying this motion model for many days, or for a long period of time. Well, the position grows unbounded, so the complexity of the density of targets, unless you keep adding more targets, the targets will spread out, and you'll end up having a lot of single target tracking problems. The problem gets simpler in that sense, but it gets quite bizarre in the sense that the velocity of the targets grows unbounded. So if you were simulating, say, the motion of submarines, well, how fast do submarines go? 10 knots, 20 knots? They'll go arbitrarily fast in a long-term simulation. So there are models that complicate things a little bit to give you some bounded characteristics. And so one thing that we can do is we can look at what's known in the literature as the Ornstein-Uhlenbeck process, which introduces a drift or a feedback term, negative feedback, that keeps that position close to the origin. So if I'm sort of wandering on the x-axis, when I'm to the left, I tend to go to the right, and if I'm to the right, I tend to go towards the origin. And the nice thing about this, if you discretize, is that first of all, you recover the nearly constant position model as this gamma goes to 0. But when gamma is non-zero, you see that the long-term behavior is bounded. So if you generate a very long-term realization, the target will always stay close to the origin, where close is defined by the process noise parameter, Q, and the feedback term. So, okay, now we now have a bounded position model. We still don't have velocity defined, but we will have velocity if we use the same idea to generalize the nearly constant velocity motion model, where we now introduce feedback in velocity. And if we discretize, we will now find that velocity remains bounded. Position still grows, but both position and velocity are well defined, and velocity stays well behaved. Okay, so this is sort of a quick summary for the engineers in the audience who like to look at these sorts of pictures. Roy Strike, who's a mathematician, tells me that he doesn't like these pictures because he'd rather just look at the equations, but I think the pictures are useful to look at. So the nearly constant position model is basically saying, okay, the state of my target is integration of noise. Nearly constant velocity motion model says, okay, the state of my target is integrated noise for velocity and then integration of that to get position. The Ornstein-Uhlenbeck process generalizes this first model and says, well, okay, the state of my target is integrated noise, but I'll introduce feedback. And the integrated Ornstein-Uhlenbeck says, well, I'll add an integrator on the end of this and have velocity and position. You could go a step further and actually close the loop in position as well on the integrated Ornstein-Uhlenbeck motion model. And if you do that, then you'll actually obtain a process that stays bounded both in position and in velocity. And here it is in continuous time, and again, I'm going to skip the math, but it's here. And you get, the only thing to note is that we now have a discrete time process that is well-defined and bounded in velocity and in position. So since it is well-behaved and bounded, you can really look at the state, you can start a realization and look at how it behaves after a long period of time. And in particular, if you start your process according to the stationary form, okay, so we have these feedback terms in position and velocity, and we have process noise. And the basic idea is, if you know how your targets are spread after a long period of time in position and in velocity space, that defines the feedback gains in the model that I wrote. So if you tell me the spread in position and the spread in velocity and the process noise, the acceleration going on, then that defines the feedback terms. And you can use this for very long-term simulations. Or for those of you who like control theory, you can think of this as a stable motion model where the poles of the system are in the left half plane. This is a viewpoint that generally, people who do target tracking generally don't worry about this. They think of short-term tracking, high revisit rates, and so they're happy to work with systems that aren't stable because they're not interested in long-term, well-behaved predictions. it turns out, again, I'm going to skip the details, but you get oscillatory behavior. If you're interested in a context where the targets are very closely spaced in position but have high velocities, you can do that. It corresponds to increasing the feedback gain, and you'll get oscillatory behavior. Okay, so we've been talking about the motion of one target. It turns out that you can go a step further if you're working in this context of well-behaved, long-term target motion models, and talk about stationarity of multi-target systems. So again, the key is to start with continuous time. There's a birth rate. Targets are coming into the scene, and targets, after some amount of time, they live for an exponentially distributed amount of time, and then they die, as dictated by a death parameter. And so you can discretize the birth rate. Basically what that means is that in some amount of time, delta t, how many targets are born? Well, roughly, the birth rate times delta t. Except that some targets, if the time step is big, some targets are born and die before the end of that time step. Some kind of sort of an infant mortality kind of thing. And you can discretize the death rate as well. And so, let me show you just a quick view of how this looks. Where's my mouse? There we go. So here there are targets being born and dying, and there's some choice of parameters for the process. But the point is that you can let this go for a very long time, and the statistics of the process in terms of the distribution and position and the velocity stay constant over time. So it's a useful model for long-term studies, long-time duration studies. Well, the military crowd would say, okay, well, this is all very interesting in mathematics, but this is not necessarily a very realistic or meaningful behavior. But the truth of the matter is that if you're doing, for example, urban surveillance, in the context of urban surveillance, it actually makes sense to say that your targets will generally stay in Ankara. Okay, some of us may leave once a day. Some of us will leave never to return. Most of us stay roughly in the same area, where roughly is dictated by that feedback parameter. So it's not unreasonable to introduce some stability in the process, because as we leave today or tomorrow, we're not going to drift arbitrarily far in space. Okay, but in order to address the issue of... So that's a stochastic motion model, which has its merits and can be useful, but this is complicated. 90 degrees is complicated. Sorry. But I want to show you just an example of this runs, of deterministic motion models. I didn't mean to suggest that stochastic motion modeling is the only thing that should ever be used. So here what I'm showing you is the tool that was used in a project that I was involved with for quite some time at NERC in maritime surveillance. And to test our multi-sensor fusion and surveillance algorithms, we wanted realistic data sets. So what we could have done was take stochastic motion models and try to put them on the globe and define sources and sinks at various ports and harbors. But that's very complicated to do. You would have to, in order to get anything somebody interested in global security would find compelling, you would have to have a pretty good knowledge of, the traffic of Rotterdam, where does it go, how often does it go to Istanbul, and so forth. And so the approach that we took instead was to say, well, we have a NATO-wide network of AIS receivers. AIS receivers are used to detect transmissions from large vessels. Vessels over 300 tons are required under international regulations to transmit, to tell the world where they are, for anti-collision purposes. Well, the idea is to take those anti-collision transponders and use the data for surveillance purposes, for security. And Now, it turns out that that data is noisy in all sorts of ways, but in order to do feasibility studies on fusion processing, the idea is to say, okay, what if we take this sensor data and clean it up and interpolate where there are gaps. So we have, these are coastal AIS receivers, so there are no receivers in the middle of the Atlantic, say. And so the idea is to take ship transponder data and interpolate across the gaps, clean up the data, and then say, now let's forget about the fact that it came from AIS. Let's treat that cleaned up interpolated data as our ground truth. After all, it's a pretty good representation of typical motion patterns. Then once we take real data, clean it up, and use it as ground truth, we can simulate data on the basis of that ground truth. AIS data and other types of sensor data, and then see how effectively we can track and fuse the multi-sensor data to reconstruct these green tracks. If you stare at this closely, you'll see some behavior that is not perfect. You'll see, for example, vessels that travel very slowly. Why? Well, because they never really did that. Maybe they went to South America, where we don't have any receivers, and then they went to Europe. Well, the interpolation algorithm doesn't know that, so it does a shortest path interpolation. But it's still a useful and fairly representative tool. And the interesting thing is that you don't need to add too many distributed receivers to start to fill in the gaps. Even though it's not a global network of receivers, it starts to approach global motion patterns. Okay, that's as much as I'm going to say about target motion modeling. Let me talk a little bit about filtering now. So filtering it's an important component of a tracking system. It's a much older, classic problem that's been studied much more extensively. And the basic idea of filtering is that we have no data association uncertainty. What's more, we have no object cardinality uncertainty. We have a sequence of measurements, and we know that all these measurements come from one object. So that's why people who do tracking in data fusion tend to say, oh, it's just a filtering problem. That doesn't, it's not intended to say that filtering is easy, but it's intended to say that the computational burden and the conceptual burden that a lot of us are focused on is missing. We know that we have a sequence of measurements and they all come from the same object. And so we can talk about doing optimal estimation, optimal filtering. Well, what's optimal? Optimal with respect to what? Well, so the basic filtering problem is one where we observe Y and we're interested in estimating X. Right? Most of you have probably seen this. You see Y and you're interested in estimating X. And you want to do it optimally. Well, in order to talk about what's optimal, we need to define a cost. How much do we penalize a difference, a deviation between our estimate of X and the true value of X? And then, since this quantity is random, it's stochastic in the sense that the object that we're interested in is described by a probability distribution, and our measurements as well, so we'll have many, many realizations, each slightly different. What are we interested in? We're interested in an estimator that minimizes the expected cost. We don't care about an estimator that sometimes does great and most times does terribly. We want an estimator that, on average, minimizes our cost. Well, now, generally in the tracking community, we look at squared errors. But hopefully it'll be useful, at least for a moment, to mention that you don't have to do that. There are other choices for how you might penalize a deviation between the thing of interest and your estimate of the thing of interest. So if you're happy with a squared error, then, well, there's a nice result that tells us that the optimal estimator, in a minimum mean squared error sense, is the conditional mean. So given what I've seen, the mean of the distribution is the best that I can do to minimize the expected cost. Now, if on the other hand you choose to penalize deviations between X and Y by the absolute difference of X and Y, then, well, the conditional mean isn't the optimal estimator anymore. Turns out in this case that the optimal estimator is the conditional median. So it's that choice such that 50% of the distribution, this is written in a scalar case, 50% of the distribution lies on one side and 50% on the other side. Now, what about if you're interested in penalizing any deviation the same way, so provided that it's a significant enough deviation? Well, in this case, it turns out that the best estimator is the conditional mode. It's the likeliest a posteriori estimate. So let's just look at an example of this. So imagine that I tell you that I'm interested in x. And what do I know about x? I know that x obeys an exponential distribution with mean 1 over alpha. And unfortunately, I don't see x, I see y. And y is exponentially distributed as well with mean 1 over x. And now I see y, and I ask you, what do you think x is? What's your best estimate of x? Well, you can work through this and write down the conditional distribution given y, and it turns out to take this form. And the point of this example is to illustrate a case where all three estimators do fairly reasonable things. So, a priori, before I tell you why, if I told you I'm interested in the minimum mean squared estimator, given this knowledge of x, well, again, if you're interested in squared errors, minimum mean squared error, you would say, well, the conditional mean, 1 over alpha. I think x is 1 over alpha. If, on the other hand, you're interested in absolute errors, you can work through the math. You'll get a slightly different answer. If, on the other hand, you're interested in the maximum a posteriori estimate, you would say, I want the likeliest. Well, the exponential has a peak at 0. So you would say, well, the likeliest answer is that x is 0. So they're different, and after you incorporate y, they all exhibit reasonable behavior as well. Why is that? Well, if you see something large, that means it has a large mean. 1 over x is large. That means x is small. And so you see that they all obey that general behavior, that if you measure something large, you'll tend to think that x is small. Okay, so just with that background now, let's forget about the other types of optimality criteria and stick to the one that we use most often, which is squared error. So in that case, well, this again is just the result that I already gave you, that the linear least squares estimator, or the minimum mean squared estimator, is given by the conditional mean. That's a nice result, but it turns out that this can be very hard to compute. In the example that I showed you, it was easy to compute. But in a lot of more practical contexts, it's not so easy to compute this. So a lot of times what we do is we say, okay, forget about the optimal estimator. Let me find the optimal linear estimator. I won't try to keep things so complicated. Just give me the best estimator that takes the measurement and does something linear to it. Affine, really, but a linear function. And so this is the result, that the linear least squares estimator for x given y is, as shown, it depends on the statistics of x and y. And many of you may have seen this. And now, in the case in which x is something that's actually x1, x2, x3, x4, it's a dynamic process, and the motion model is linear, and if the measurements that you observe, y1, y2, y3, y4, are linear as well, then it turns out that this object here can be written recursively. You're estimating x3 based on y1, 2, and 3. And then with x3 and y4, you estimate x4. So you do it recursively, which is much more computationally efficient, and that's the Kalman filter. So I'll just state this. I won't bother going through the Kalman filter. But now, the other nice thing to note is that if, in addition to linearity, you have Gaussian process noise and Gaussian measurement errors, then the Kalman filter isn't just a recursive way of doing linear least squares estimation. It's actually a recursive way of doing least squares estimation. It gives you the optimal estimate. So let's look at just a small example of this. So let's say that I tell you that I want to know x, and I give you n measurements. Z0, Z1, Z2, Z3 through Zn minus 1. And each measurement is x plus noise, where the noise is uniformly distributed, from minus a half to a half. And I asked you, on the basis of these n measurements, what is the best estimate for x? Well, you might say, well, okay, the motion model is linear because the target's not moving, it's stationary. And the measurements are linear. And so I'm going to use the common filter because, well, the measurement noise isn't Gaussian, but that's okay. What if I replace this uniform distribution by Gaussian distribution with the same bit? And just use the common filter because I know it and it's not so complicated. You could do that, and you could write it in recursive form, or you could write it in bash form, which is what I've done here. And the nice thing, one nice thing is that the Kalman filter does something very reasonable. It basically says, okay, I have n measurements, I'm going to average them. And you can see that the error in this estimate decreases as 1 over n. So that's pretty good. But since we have violated the optimality assumptions of the Kalman filter, we might be able to do better. And in fact, for this example, you can do better through a recursive estimator that keeps track of the largest and the smallest of the measurements that you've observed up to some time. If you think about it, you can think of these measurements as bounding what x might be. And n measurements, essentially, you look at the intersection, and there's a resulting region in which the target must lie. And so if you take the midpoint of that intersection region, that turns out to do better than the Kalman filter. And it's because we don't have Gaussianity. So it's just something to keep in mind. Now, in a lot of cases, we say, well, it doesn't matter, and we proceed with the Kalman filter. But it's good to know. Good to know that it's not always the optimal thing to do. What time did I start with this? I always forget my starting time.
2:10.
2:10. Thank you. Okay. I don't want to spend too much time on this. Okay. Well, filtering. I just have one slide to mention that for those of you who are interested in this sort of thing, you can imagine taking one step away from linearity. And one way that you could do this is to say, okay, rather than having one linear motion model, I'll have n linear motion models. And my target is sort of switching from one linear motion model to another linear motion model. Well, you now have a non-linear motion model, but there are efficient ways of mixing and managing n filters in parallel. And for those of you that are interested, I would just encourage you to look at the interacting multiple model filter. Okay, so that's as much as I want to say about filtering, where by filtering I mean, again, sequence of measurements, and we know there's one object and they all come from that same object. So let's make things a little bit more complicated, but without going to the full-blown tracking problem yet. Let's talk about multi-target filtering. What do I mean by multi-target filtering? What I mean is, I know how many objects there are, and I have a perfect detector, where by perfect detector I mean no false alarms and no misdetections. So I look, I know there are 3 objects, and I look, and I have 3 measurements. Then I look again at the next time step, and I have 3 measurements. So I don't know which measurement goes with which, but at least I know that there are 3 targets. In the tracking context, you might think of this as track maintenance, where I'm not worried about initiating a track. I'm just interested in keeping alive some number of tracks that are already confirmed through some other process. Well, a lot of techniques exist, and let me just talk about these very quickly. One is the statistical nearest neighbor that says, and I've illustrated this with a 2-target example. Imagine that I have 2 tracks, and in the current scan I have 2 measurements. Well, and I don't know which measurement goes with which track. Well, one thing you could do is to say, well, okay, I'm going to order my tracks according to some rule. For example, the track that looks the best, or that has been around the longest, or that I'm most interested in, according to some criterion, I want to satisfy him first. I'm going to give him his statistical nearest neighbor, and I say statistical because imagine that there's an error ellipse around the estimate of where the target is and around each measurement. So it's not really the closest it's not in Euclidean space. It's called the Mahalanobis distance. But the idea is, basically, I give the first track what he wants, And then I give the second track what's best for him, and then I would go on to the third track and so forth. And that's very simple, but it turns out that you can do better if you go to what's called a global nearest neighbor and say, no, I don't want to satisfy things sequentially. I want to satisfy my n tracks with the n measurements by minimizing the overall cost. And you can see that in general, you'll get a slightly different answer. Now, in any one realization, this nearest neighbor approach may do the best, but statistically, the GNN is a little more complicated, but it performs better. You could go another step up in complexity and say, well, you know, my error ellipses are really big. I don't know which measurement comes from which target. I'm flipping a coin. I have no idea. Well, so what you could do is go to a soft data association, where you say, okay, I'm going to give each of my tracks a weighted combination of the measurements to reflect the inherent uncertainty of the problem. And again, statistically, you'll do better at the cost of some complexity. And you could go another step up in complexity and performance by saying, well, I don't really like this soft association approach. I in the end, want to know which measurements went in which target into which track. So I prefer a hard data association approach. But in order to contend with the uncertainty, let me wait until another scan of data, or 2 more scans of data, or 3. And with the benefit of the additional scans of data, let me try to make a good, hard decision about what happened in the past. So, just showing you one example here. This is with 2 targets that are moving in one dimension. So time is going forward along the x-axis. And they're both moving according to this Ornstein-Uhlenbeck process, so they stay close. And how close is dictated by how you tweak the realization. But they'll stay close for as long as you want them to stay close. And so that sort of illustrates the benefit of these stationary processes, because otherwise, if you wanted 2 targets to follow a stochastic motion and stay close, you'd be challenged to do so. Okay, but the point to note is that, so we have 2 black lines representing the true target motion. And the ideal solution is the one where I tell you, okay, this measurement comes from target 1, that measurement comes from target 2. So I have 2 independent filtering problems. That's the best that you can do. That's the blue solution. The probabilistic data association filter, you can see that it suffers when the targets get close. Why does it suffer when the targets get close? It suffers what's called coalescence. And the basic idea is that if I have 2 tracks, and I have 2 measurements, and I give each track a weighted combination of the 2 measurements, well, what's going to happen? The presence of the other object bothers me, because I use a little bit of his measurement. And the net result is that at the next step in time, he and I are a little bit closer. Well, now we're a little bit closer, and at the next step in time, we're going to use an even more similar weighted combination of measurements, and we're going to get closer still. And will eventually fall on top of each other. And unless you introduce some logic on top of the probabilistic data association filter, once they're on top of each other, then there's no mechanism to pull them apart. Well, the multi-hypothesis tracker suffers the opposite effect. It suffers track repulsion. Well, why is that? Well, that's because, imagine again the case where I have 2 targets, 2 tracks corresponding to 2 targets, and there's a current scan of data with 2 measurements. Well, if I'm on the left, I'm on the right of you, I'm always going to grab the measurement on the right, and you're going to grab the measurement to the left. Even though statistically, sometimes I generate that measurement, and you generate this measurement. But since we wanted, well, the MHT solution turned out to be the same as the nearest neighbor solution, so we can talk in terms of nearest neighbor. I'll grab this measurement, and you'll grab that one. If we're close, that will introduce an inherent bias. I will always grab the measurement to the right, even when it's not my measurement. And you can see that here, that the MHT it introduces this repulsion only when the objects are close. And the problem gets, as the targets get close, this repulsion effect increases. So I'll come back to this. What I'm going to mention now, just for a second, the equivalence class MHT. But suffice it to say for now that one of the ways that you can counter this repulsion that exists in hard data association trackers is to introduce some swaps of measurements. in a controlled fashion. And the basic motivation to do so is that if I start swapping some measurements, I'm doing something suboptimal. So the best thing to do would be always give the target on the right the measurement on the right. Always give the target on the left the measurement on the left. That would be the statistically likeliest explanation of the data. But what I could do is, you know what, I don't necessarily want the single best solution. I want a solution that is individually worse than the global solution, but is representative of a class of solutions that are very similar, and that taken as a collective whole are more likely than the single likeliest solution. So if I have 10 sensors looking, and they each generate 2 measurements, and I swap a couple of measurements, well, there are 10 choose 2 ways that I can swap a couple of measurements. Now, depending on how I swap the measurement, I'll get a slightly different solution, but not so different. So there are a lot of suboptimal solutions that are very similar, and if I look for the class of solutions that's likeliest, it turns out that you don't suffer this repulsion. And so there should be a realization of it here, where you see that, okay, so this is a little bit zoomed in from what I was showing you before. Now you can really see the repulsion in the MHT. You can see that the 2 tracks are further apart than the underlying black ground truth. And you can see this equivalence class MHT, which does a reasonable job. Occasionally the tracks will swap. So it certainly doesn't do as well as the ideal filter that always keeps track 1 on target 1 and track 2 on target 2. But it doesn't have coalescence and it doesn't have repulsion. And I'm going to skip the simulation details. I think we all make this mistake of putting more than we possibly can talk about. And we never learn from our mistakes because we go through these presentations and we always think it'll be different and that we can talk faster. Now, Peter Willen, who will talk next, he can talk really fast. So he can cover 3 times as many slides as me and do it very well. But I'm much slower. Okay, just another example. You see that occasionally this equivalence class MHT swaps. And so since it swaps, and in general, with all of these approaches, how do we say which of these schemes is better? In a classical filtering problem, I showed you the metric before, squared error. Here's my estimate, here's the target, what's the estimator that minimizes that difference? But if I have n estimates, and in general, m targets, what's the criterion? So I won't go into the details, but it turns out there's this mean optimal subpattern assignment. It basically says, well, okay, of all the ways that I can associate my estimates to the true target locations, let me find the one that minimizes the costs and use that to say how good my solution is. And according to that metric, which allows you to deal with the fact that sometimes tracks swap, according to that multi-target generalization of minimum mean squared error, this equivalence class MHT does better than some of the older approaches. Still doesn't match the ideal filter, of course. Okay, so now let me start. I probably won't be able to work through this next section, but let's just start talking about it. So now I want to go up to the next step of complexity, the general tracking problem. This is where, well, what's the general problem? Unfortunately, let's get this. Okay, what's the general tracking problem? It's very high level. I'm going to give you a sequence of sets of measurements. I'm going to give you some measurements at time 1. I'm going to give you some measurements at time 2, time 3, and so forth. That's what I mean by Z superscript K. Sequence of measurements. And what do I want you to do? I want you to tell me, I want you to give me a solution, xk, a solution that lives on the same time interval. And this xk looks deceptively simple here. It's actually a very complicated object. How many xk's are there? There's a whole lot of them, because basically, this xk tells me when targets are born. Maybe there are no targets. But when each target is born, when each target dies, and the trajectory associated with each target. So in the general, all the tracking approaches that you'll be hearing about today and tomorrow take very different approaches, but to do the same fundamental thing, which is, well, I want to come up with a posterior distribution on this tracking solution, given what I've observed. Now, all the trackers also, they're not going to give you, oh, here's a distribution for what happened. They're going to give you one answer. But they're going to, in some way, attempt to take a good function that is based on this posterior distribution. Well, I want to talk about, just very briefly, about the hybrid state approach to the problem, which leads to the MHT. And the basic idea is to say, well, okay, this is really hard to compute. And so what I'm going to do is I'm going to write that as a sum of posterior distributions, not just over the state trajectories, but over a discrete state, which I'm going to introduce. What's a discrete state? A discrete state gives me sort of a discrete explanation for what happened. It says, this target was born at this time and died at that time. This target was born at this time and died at this other time. These measurements are false. These are the measurements that go with target 1. These are the measurements that go with target 2. That's it. I give you a complete explanation for which measurements are good, which measurements are false, and which measurement goes with which. Well, if I give you all of that information, if I tell you all of that, then if I tell you which measurements are false and which measurements go with which, I've set up a sequence of filtering problems for you. Now all you need to do is say, okay, these measurements go together, let me filter on them. These go together, let me filter on them. So essentially, if I tell you the discrete state, then in addition to giving you the data, I tell you what to do with the data, you have a filtering problem. Now unfortunately, in order to get at what we really want, I have to average this answer over all the possible discrete explanations of what might have occurred. So this is a huge sum, but it's a useful way to think of decomposing the problem. And I'm not going to go through the details, but all I'm going to tell you is that, let me go back a slide, is that this is the key thing of interest. I want a distribution on the discrete explanation of the world given the data. And so, since I want to do this recursively over time, it turns out that I need to be able to write probability of qk given zk as a function of what I knew at the previous time step. And so the details I'm going to skip. But the bottom line is that you can do it. You can write the posterior distribution as a function of the previous posterior distribution. And some other terms that tell you, okay, some targets died, and some targets didn't die and weren't detected, and some targets didn't die and were detected, and here's the score, the filtering score that goes with them, and some other targets were born. So you can do that. And so what's MHT? What's multi-hypothesis tracking then? Well, multi-hypothesis tracking, it looks at this decomposition and it says, well, okay, but I don't want to give you a full distribution as a solution. I want to give you one answer. So I'm going to give you the expected xk given zk, but that's still too complicated. I'm going to bring the expectation into the summation, and I'm going to give you the expected solution for only one qk given zk, the likeliest, where I compute the likeliest with the benefit of a few scans of data. So what I'm going to do now, very quickly, is show you an example of this. And so let's just look at an example. Imagine that I have two tracks, two confirmed tracks. And now I have a scan of data. And in this scan of data, I have two measurements, R1 and R2. And they're both close to target 1. So either of them could be an update to target 1, but perhaps neither is. And imagine that R1 is also close to target 2. So R1 could be an update to target 2, but perhaps not. And R1 and R2, they could both be the start of something new, a new object that appeared on the scene. Now, if I wanted to solve a global nearest neighbor problem, at this point I would make some decisions. I would say, okay, here's the likeliest explanation, let me choose it. Well, we don't want to do that. We want to wait for another scan of data in order, hopefully, to make a better decision. And let's assume that in this, boy, these points moving around, they look a lot like the Ornstein-Uhlenbeck process. Anyway. Hypnotic. Okay, so anyway, so with this second scan of data, imagine that there's a measurement R3 that's close to R2. So you see an R2 here and an R3, R2, and R3. Now that we have this second, oh, and I should say that in this example, imagine that after 2 missed detections, we terminate a track. So the first thing to say here is that this is a track-oriented multi-hypothesis tracking approach. What do I mean by that? In the old days, if you go back to the original work by Reed in 1979, he used hypothesis-oriented MHD. What does that mean? That means that you explicitly enumerate all the possible hypotheses, in principle, all possible explanations of what's going on, and you pick the likeliest. In this case, what would that mean? That would mean that your list would, for example, include T1 goes with R1, and T2 stays by itself, and R2 goes with R3. That's one global hypothesis. You could list many others. Even for a simple problem like this, it's a lot of things to manage. I don't want to write a list of global hypotheses. I want to formulate the problem in such a way that global hypotheses are implicitly defined. I can list them like the one I just identified, but I don't want to list them. But they're implicitly here. And while all I worry about are these local track hypotheses. So now what do I need to do? Now, there are many techniques, by the way, to control the growth and the pruning of trees. This is what makes one MHT different from another MHT. For example, if I really wanted to do the right thing, at this first scan, when I either update target 1 with measurement 1, or I update it with measurement 2, or I say he's still alive but he didn't die. But it's also possible that he died. That would be another branch. I've introduced some logic here where, no, I don't spawn both hypotheses. I only spawn the coast still alive hypothesis. But at the next step, again, I don't want to spawn both, but if I haven't seen him for a long time, I'm only going to spawn the death hypothesis. So on top of the theory, in the end, we put rules to manage our hypothesis space. How much do we want to let the hypothesis space grow, and how do we want to prune it? Wolfgang, I don't think he went into the details of it, but the approach that they generally take at FKIE involves merging of track hypotheses, or pruning when the likelihoods are low. What I'm showing you in this example is what's called end-scan pruning, which means with some delay in time, cutting away the branches that aren't consistent with the likeliest solution. What's the likeliest solution? Well, so what this means is I want to look at these leaves on these trees, and I want to identify a good solution. What's a solution? A solution is a vector x of dimension 10. And each element of x is either a 1 or a 0. 1 means I take the branch. 0 means I don't want that branch. So I want to choose this vector x so as to maximize an objective. Well, I'm not going to tell you what C is, but it's a vector of costs having to do with some of the terms I showed you before. Probability of being born, of still being alive, of having taken a particular sequence of measurements. But the bottom line is there's a cost associated with each leap, or a reward. We're maximizing, so here it's written as if it were a reward. Okay, so we want to choose x to maximize this quantity. That's the mapped solution. There are some constraints, however. Why are there constraints? Well, I need to tell you something about what happened to target 1. So I need to choose one of these 4 branches. That's represented by the first constraint equation. I can choose whatever x I want, but it has to have the property that either x1 or x2 or x3 or x4 is 1, and the others have to be 0. And similarly, we have to say something about what happened at track 2, and I have to use measurement 1 exactly once. So I should choose either branch 1, or branch 5, or branch 7. That gives me a constraint of using measurement 1, and of using measurement 2, and of using measurement 3. It's an integer programming problem. A lot of techniques exist to solve it. Lagrangian relaxation, simplex method. But the bottom line is you solve it, and then you round off your answer to maintain feasibility. This I'll skip. How much can I go through? Not very much. Well, in any one data set, let me just say this, that in any data set, is multi-hypothesis tracking a good thing to do? And is there a benefit in reasoning over more scanned data? Well, as usual, in any given realization, anything can happen. But statistically, multi-hypothesis tracking with deeper hypothesis trees will give you better tracking performance. Here's an example from a sea trial from a number of years ago at this point, with the Dutch submarine, where we see that without multi-hypothesis tracking, this tends to happen, that when the target is maneuvering in a region of heavy clutter, we lose the target. If we do use multi-hypothesis tracking, we're better able to maintain track continuity and to distinguish between the target and the stationary clutter track. Here's just an example of this, if I can. Just to show you what this. So things look much more cluttered when you look at a cumulative display because you're accumulating false tracks. But typically, what's of interest to an operator is the average number of false tracks on the screen at any time. Okay, and by the way, I've been focusing on kinematic measurements, but it turns out that one of the ways that you can achieve, at least in part, the benefits of multi-hypothesis tracking is by taking more out of your data, not just range and bearing measurements, say, so kinematic measurements, but also feature information. So here's this is SNR data from that example that I just showed you with the zigzagging target, where the target is maneuvering close to a fixed feature. So I have two targets that are physically very close. One is maneuvering, so he's violating drastically the underlying motion model. It's very difficult to know which measurements go with which target. But it turns out that if you augment your measurement space and look at the SNR of the contacts, then although the data is very noisy, you can see that there's some separability between the time series of SNR measurements associated with the target and the time series of SNR measurements associated with the fixed feature. So I think I'll stop here, but I'll just mention, and I'll come back to this tomorrow, that just like there's no guarantee that deeper hypothesis trees provide benefits, but they generally do, the same is true of adding more sensors. Generally speaking, if you add more sensors of comparable quality, your tracking solution will improve. But there's no guarantee that that's the case, and so I'll talk more about that tomorrow. And of course, as you add more sensors, you add complexity to the problem, and so you need to look at things like distributed MHD. I'll tell you a little bit more about that tomorrow.